We go over chemistry 1000, 2022 academic year. How many moles of carbon atoms are needed to combine with 4.87 moles of chlorine molecule to form the substance carbon chloride? Now, this carbon, of course, that wouldn't be just carbon chloride because you can see we have got two carbons and six chloride. So I don't know if I can read it as dicarbon hexachloride like that. So how many moles are we going? So how many moles of what carbon do we require to combine with 4.87 moles of chlorine? So let's see first how the reaction or the equation is going to look like. So we're going to have carbon reacting with chlorine. We know chlorine always exists as a diatomic gas, and this is forming carbon with a 2 and then chlorine with a 6. So to balance this reaction, we're going to put a 2 here, and then to balance the chlorine, we're going to put a 3 here. So we've already been given 4.87 moles of chlorine. This is 4.87. Now we want X, how many moles of carbon are going to react. But we know that the number of moles of carbon divided by the coefficient, which is 2, should be equal to the number of moles of chlorine divided by the coefficient, which is 3. Okay, so now in this case, we are going to do the cross multiplication. So that means number of moles of carbon is going to be, multiply this 2 in the denominator with the number on top. That will be 2 number of moles of chlorine divided by 3. So this is going to give us 2 multiplied by the number of moles of chlorine, that is 4.87, and then divided by 3. So let's see what we get. 2 multiplied by 4.87, then divided by 3. So this is about 3.25. So that is the answer. That is D. By the way, this option wasn't there, so when the paper was being written, they asked for a change. That's why you're able to see that value on top, 3.25. All right, next question. Question number 2. A 2 grams, that one also was changed. A 2 grams sample of sodium hydroxide was dissolved in water to produce a total volume of exactly 200 cubic centimeters of solution. What is the molar concentration of sodium hydroxide? So I've got 2 grams sample of sodium hydroxide which was dissolved in water to produce a total volume of 200 cubic centimeters. What is the molar concentration of sodium hydroxide? The first thing first, we need to find the molar mass for sodium hydroxide. So the molar mass we have got in sodium hydroxide, we've got 1 sodium, and then the mass of the sodium, that should be 23. Let me just get to confirm that from my periodic table. Peradventure I have missed it. All right, so the molar mass for sodium, that is a 23. Of course, I'm using a rounded off timetable. So depending with the timetable that, I mean periodic table, not timetable. Depending with the periodic table that you've been given, make sure that you get to use that same one. If it is 22.9 watt, get to use that same value. So this is 23, and then oxygen in sodium hydroxide, I'm going to use 16, and then hydrogen is a 1. So when we get to add this, of course, 23 plus a 1, that is a 24. So what we have is 24 plus 16, which is a 40. Okay, that's the molar mass for sodium hydroxide. So the number of moles of sodium hydroxide is mass over molar mass. The mass is 2 grams. The molar mass is 40. So 2 divided by 40, that is going to give us 0.05 moles. All right. So we have found the moles, but we want the molar concentration. Molarity is given by number of moles over volume. Okay, so the number of moles 0.05, and then the volume, we are dissolving in what? when we got to dissolve this, the volume was made up to, the volume became 200 cubic centimeters. That's the total volume. Now this one is in cubic centimeters, but the answer is supposed to be in molar. Molar is mole per decimeter cubed. So if we need to convert this centimeter cubed to decimeter cubed, we need to just divide by 1000. So it will be 2000, 200 divided by 1000, which is just going to be 0.2. So we're going to divide this value by 0.2. So let's see what we get to find. So this is going to give us 0.25. So this is the answer then for this question. So whenever you are converting from cubic decimeter to cubic centimeter, you multiply by 1000. When you're converting from cubic centimeter to cubic decimeter, you divide by 1000. Question number 3. Three 1 liter flasks are filled with hydrogen, oxygen, and neon, respectively. A standard temperature and pressure at this is at standard temperature and pressure. Which of the following statements is true? Each flask has the same number of gas molecules. The velocity of the gas molecules in the same is the same in each flask. The density of each gas is the same. There are twice as many oxygen and hydrogen molecules as neon atoms. All right. So we have got 3 containers. They are all 1 liter. Now one is filled with hydrogen gas. The other one is filled with oxygen gas. The other one is filled with neon. Okay, now if you get to look at option 1, what is option 1 saying? Each flask has the same number of molecules. How do you know the same number of molecules? The only way you can tell the same number of molecules is you need to know the moles which have been added in these containers. Okay, so if they are all filled up, let's say it is they are all filled up at that point. We don't know how much mass of hydrogen is going to be able to fill this container, how much mass oxygen is going to be able to fill up this container, and how much mass of neon is going to fill up this container. Since they are going to have varying masses, or let's say they are going to, it is the same mass that is going to be able to fill all these containers, same mass of hydrogen, same mass of oxygen, same mass of neon. But if you get to consider number of moles given by mass over molar mass, each of these are different substances, meaning that they've got different molar masses, and so their number of moles are going to be different. If they've got different number of moles, meaning that each flask has different number of gas molecules. How different the number of gas molecules? 1 mole is equal to 6.0 times 10 to the power 23 molecules. So since they've got different moles, meaning that they're going to have different molecules. So this one cannot be true. I'll go to option C. The density of each gas is the same. Well, let's say the mass of these substances. Now, obviously, since you can see hydrogen is much lighter, right? Oxygen gets to follow up, and then you have got neon. So they've got different masses. So there is no way they can have the same density. Okay, they can't have the same density when you fill up these substances. Get to consider this. You can have a sack, like a sack. If you get a sack, you get this container, you fill it with sand, and then you get this same container, you fill it with feathers. Which one do you think is going to be heavier? So this container with sand is going to be much heavier. Why? Because sand has got a higher density. So same with these, we're feeding them with different substances which have got different molar masses. So obviously they will not have the same density. If you look at option 2, there are twice as many oxygen and hydrogen molecules as neon. Now if you say there are twice oxygen and hydrogen as much as there is neon, meaning that if neon is 2 moles, meaning that oxygen and hydrogen they are going to be 4 moles. And how can these two be the same and they both be twice than neon, as though they have got the same molar mass, or so the same mass was added? So that is obviously not true. Okay, so the velocity of the gas molecules in the containers is the same. Okay, so the speed at which they are going to be moving, since they are all gases, okay, since they are all gases, you are going to get to assume the ideal you get to assume ideally that the velocity at which they are going to be moving in that container is going to be what? The same. Okay, because when you get, all of these are gas molecules. So because they're all gas molecules, meaning that the exposure that they are going to have in these containers, they are all going to be able to freely move in these containers just by themselves like that. All right. So the velocity of the gas molecules in the same is the same in each flask. All right. Question number 4. Which of the following refers to the amount of energy required to remove an electron from an atom? Atomic radius. Atomic radius is the distance of an electron from the nucleus. So this is not true. Electronegativity. Electronegativity is the ability of an atom to pull, okay, to pull electrons to itself when it is being shared in a bond. So this is not true. Electron affinity. Electron affinity is the energy that is released, okay, when an electron is drawn closer or when an electron is taken in by an atom. And then ionization, to ionize is to remove, is the energy that is required, okay, to remove an electron from an atom. So this is it. Which of the following violates the octet? Which one violates the octet? Now if you look at ammonia, ammonia is like this. If you draw the Lewis structure, it has got two lone pairs here, so it doesn't violate the octet. If you look at, how did I draw this structure? Maybe you need to know how to draw the structures, because if we just say this one doesn't violate the octet, you might not be able to understand. So if you look at ammonia, we are going to look at the valence electrons. Valence electrons, we've got electrons in the outermost shell. First, nitrogen has got, is in period 5, in group 5, meaning that it has got 5 electrons in the outermost shell. And then we have got 3 hydrogen, and each is in group 1, meaning 1 electron in the outermost shell. So if you get to add this, this will give you 8. So obviously nitrogen is supposed to be the central atom. We have got 3 hydrogen. I'm going to put one this side, one this side, one this side. Okay. And then each bond that you're able to see has taken in 2 electrons. There are 3 bonds, meaning 6 electrons have been taken. From the 8, I mean, are remaining 2 electrons, and obviously those are going to come on the nitrogen. So nitrogen has got 8 electrons in that atmosphere: 2, 4, 6, 8. And each hydrogen has 2 electrons, okay, in that atmosphere. So that is for this one. And then if we get to go to the next one, boron trichloride. Well, starting with boron, boron is in group 3. So we're finding the valence electrons also for this one. So meaning that it has got how many electrons in the atmosphere? It has got 3 electrons in that atmosphere. And then I've got 7 electrons in the atmosphere for each chlorine, and there are 3 chlorines. 7 times 3, that is 21. 21 plus 3, that is 24. All right. So we are talking about 24 electrons in the outermost shell. So these are the electrons that are going to be shared. So first I'm going to write bromine. I'll put a bond with chlorine, a bond with chlorine, a bond with chlorine. And then this means that we've used up how many electrons? 6. Okay, because of 3 bonds. From the 24 we've used up 6, meaning that 18 electrons are remaining. Okay, from the 18 electrons that are remaining, each chlorine to be stable, it only has 2 electrons here. It needs 6 more electrons. So 1, 2, 3, 4, 5, 6. Each needs 6, and there are 3 of them. So 6 times 3, that is 18. Meaning that all these 18 which remained are going to just be taken on by the chlorines. Now notice that boron will only have 6 electrons in the atmosphere. So it violates the octet. All right, it violates the octet. And mostly when you get to look at atoms such as boron, these atoms mostly get to violate the octet. All right, and when you consider also some atoms which are in period 3, like phosphorus, those also are sometimes able to violate the octet. All right, so the answer is boron chloride. That's the answer. In question number 6, in a galvanic cell, electrons flow from the dash to the dash. Okay, electrons flow from the, so from where to the to where? Where do electrons flow from? Now, when we get to look at this one, how are electrons going to be able to move? Let me first draw a diagram we see. So I've got this compartment and another compartment. So I've got an electrode in these two compartments. So electrons are going to be able to move like that. I'm going to put a voltmeter here. I'm supposed also to put a salt bridge. So where electrons come from, this region is going to be negatively charged. Okay, and where electrons are going, that region is positively charged. I'm saying where they are going for a galvanic cell is negative. And why would we say that? Because when you get to consider this, like, you know, you get to contribute when you have got more, right? So electrons are coming from where there are a lot, and where electrons are a lot, obviously that place should be what? Negatively charged. That is why I'm saying that. Okay, but when for a galvanic cell, the other way around is going to be for an electrolytic cell. Okay, question number 7. An electrochemical cell stops working after some time because electrode potential of both the electrodes becomes zero, electrode potential for both becomes equal, one of the electrodes is eaten away, one of the electrodes increase in mass. Of course, it is true that one electrode is going to be increasing in mass, one electrode is going to be eaten away, okay? But the thing that gets to happen really here is that as electrons are flowing from one compartment going to the other compartment in that direction. Okay, remember this, we're talking about an electrochemical cell. An electrochemical cell is basically a galvanic cell. So as electrons are flowing in that direction, what is going to be happening is that one compartment is what? One compartment is decreasing. Okay, that decrease in one compartment, that decrease which is happening is going to make sure that it gets to chew up this other compartment. And by the time the compartment is like completely chewed, it will be now called a dead cell. Okay, a dead cell has got in other words, electrons, all the electrons have moved. Okay, all the electrons have moved, they've gone the other side. So the only way uh, this cell is able to work is that electrons have to be reversed in that direction. So when all the electrons have flowed gone to the other direction, that cell is dead, and so it stops working. All right. So what can we say here? One of the electrodes is eaten away. So when one of the electrodes is eaten away, this is going to make the cell to stop working. Why is it going to stop working? Because where are electrons going to flow like through? Okay, where are electrons going to flow through? So that is the reason as to why this is going to happen. All right. I hope that is clear. Question number 8. A basic buffer solution can be prepared by mixing. A basic buffer solution can be prepared by mixing. All right. So when you are preparing a basic buffer solution, well, firstly, we need to know what a buffer solution is. So a buffer solution is a solution that contains an acid and its conjugate base or a base and its conjugate acid. Okay. All right, so as you are doing this, now what you are going to be able to put is that you don't use strong acids and you don't use strong bases. What you need to make sure you use is that you get to use a weak acid or a weak base, and then it's going to have its conjugate. All right, for example, hydrogen fluoride. This is a weak acid. So its conjugate is going to be, the hydrogen is going to be lost, that is going to be F minus. Okay, this is a conjugate base because it was an acid. So just to keep this compound, we're going to react with the sodium. So I'm going to say sodium fluoride. This is a conjugate base. This is the weak acid. Now, when you're this is more acidic, like you started with an acid. Now, when you're preparing a basic buffer has a pH, and it is prepared by, I mean, it has got a small pH. Okay, it has a basic pH, and it is prepared by mixing a weak base and its salt with a strong acid. Right, a weak base and its salt. Okay, so that is how you get to prepare a basic buffer, a weak base with its salt. So that is option B. Question number 9. The thermochemical equation 1 and 2 are shown below. Which of the following is an accurate classification of these two reactions? Okay, if you look at the first reaction, the energy is on the product, meaning that it is exothermic. For the first one, the energy is on the reaction, meaning that it is endothermic. Okay, so 1 is exothermic while 2 is endothermic. So that is the last option, D. So whenever you see energy on the product, that should be exothermic because energy is released. At times we're going to see delta G, I mean delta H is negative. Just know that that's exothermic. If it is positive, that's endothermic. 10. Which equation corresponds to correct definition of standard enthalpy change of formation of calcium chloride? Standard enthalpy change of formation of for calcium chloride. Okay, so when you are forming calcium chloride, we need to know that calcium chloride firstly is a, a solid. All right, calcium chloride is a solid. Now you're going to react chlorine. Chlorine is a gas. You're going to react with calcium. Okay, calcium is a solid. And when you get to react those, now you're going to form calcium chloride, which is a solid. And standard enthalpy change or formation, you're supposed to form one more of product. Okay, so here you can look at the state symbols. Of course, gas is correct, solid is correct, but this isn't liquid. Okay, here chlorine liquid, of course that's not true. Okay, for B, gas, solid, this is a solid. Okay, this is okay. And then for the next one, chlorine is a gas, calcium is not a gas. Okay, so that is not it. So the option is B there. Consider the thermochemical equation below. So there we have the thermochemical equation. Water which is a solid goes to water which is a liquid. What would be the enthalpy change for the thermochemical equation shown? So how do you get to find the enthalpy change? The enthalpy change of the reaction is given by, okay, so here we've been given the reaction that is going forward, like from solid to liquid. Okay, we have a solid to liquid. But now we want to find the enthalpy change. Enthalpy change when you start, now you put a 2 in front of the reaction. Okay, even here you put a 2. Now we need to know that when you multiply a reaction by 2, you are also going to multiply the enthalpy by 2. So since this reaction we started with the solid to liquid. This is also solid to liquid. But this one had the 1 in front. This one has a 2, meaning that you only multiplied by 2. So if this is x kg, then this is going to be 2x kg. So just multiply by 2. That same constant that you multiplied the reaction with is the same constant that you multiply also the enthalpy with. Question 12. A sample of freshly pressed apple juice has a pOH of 10.24. Calculate the concentration of hydronium ion. Okay, a sample of freshly pressed apple juice has a pOH of 10.24. Calculate the concentration of hydronium ion. Now we need to know that first starting with the pOH. pOH plus pH is equal to 14. Okay, so since we've been given the pOH, we can find the pH, and that is going to be 14 minus pOH. pOH they've given us, that is 10.24. So let's see what we get. 14 minus 10.24. That is going to give us about 3.76. This is the pH. So given the pH is given as negative log of the hydrogen concentration. So hydrogen concentration is equal to hydronium concentration. All right. So pH will divide both sides by negative. That will be negative. pH is what? We found 3.76. And that is going to be log hydrogen concentration. To find hydrogen concentration, we know that this log is in base 10. So I'm going to say 10 to the power negative 3.7 is equal to the concentration of hydrogen. The concentration of hydrogen is going to be equal to 10 to the power negative 3.7. Okay. So 10 to the power negative 3.76. So that is going to give us about 0. I left out a 6 here, so even here there's a 6, 0.00017. So this is going to be the concentration, which you can write in standard form. This is point moles 1, 2, 3, 4. So that is 1.7 times 10 to the power negative 4 molar. So that is the concentration, which is this one here, C. Question number 14. A large value of Kc means the equilibrium there is. Okay, how do you get to calculate the Kc? So I'm going to give three reactions. Let's say A goes into B, and then let's say we have got again A goes into B. We also have A goes into B. But let's say for the first reaction, the concentration on the reactant is 2, on the product is 4. For this one, the concentration here is 4. Let me say 3, and the product is also 3. For the other one here it is 4, and then here it is 2. So for the first reaction, Kc is given by concentration of product divided by the concentration of reactant. So 4 over 2, that is going to give us a 2. For the second one, the Kc is going to give us 1. Okay, that means that something is at equilibrium. And then for the last one, Kc, the product divided by reactant, that will give us 1 over 2. Okay, this means that a large value of Kc here, this is the largest value, means that you have got more product and less reactants. Okay, less reactants and more product. So that is A. Question 15. The condition of temperature and pressure under which the gaseous, liquid, and solid phases of a substance can coexist is called. The condition of temperature and pressure under which the gaseous, liquid, solid of a substance can exist is called. For example, if you get to look at the phase diagram for water, you are going to have a point where it is like this. You have got a solid, liquid, and a gas. This point here, when water is existing in all the three states of matter, that is called the triple point. 16. Which response includes only those compounds that can exhibit hydrogen bonding. So we've been given these different five compounds. So those compounds that can exhibit hydrogen bonding should have a free a hydrogen, okay, hydrogen that can interact with the other substance. Okay, so which response includes only those compounds that can exhibit hydrogen bonding. So you also get to look at how the atoms in that substance are. Okay, is there any, are those molecules like charged? So also look at those molecules if they are charged or not. If you look at the first one, you have got AS, you have got three hydrogens. So one is going to be here, one is going to be here, one is going to be here. Okay, so basically this molecule, if you get to look at it, it is going to be mostly non-polar. It's not going to be polar, not charged. If you look at H, or let's say if it is polar because of the way it is, let's say the net dipole in this direction cancels with the net dipole in this direction, meaning that this one is going to remain with the net dipole in this direction, meaning that this compound is going to be polar. But if you look at H2Te, so we're going to have Te, okay, then you are going to have H this side and H this side. So these two H's, they are going to, their dipoles are going to cancel each other. So this is not going to be polar. So if you again look at this one which is here, you have got CH3 NH2. So if we write C with three hydrogens, hydrogen here, hydrogen here, hydrogen here, and then you have got a nitrogen with two hydrogens, one hydrogen there, okay, and then another hydrogen. So if this is how the molecule is going to be, I don't know if that is going to be the drawing. But when you get to look at this molecule, is it going to be polar or not? Okay, it can be polar or not polar at any time. I don't know how we are going to even draw this structure, but we are not more interested in drawing. We can draw the Lewis structure if we so wish to by finding the valence electrons of this substance. But as we earlier even commented on this one is more not going to be a polar molecule. If you get to look at this one, nitrogen is more electronegative than carbon. So because of this, there's going to be some polarity going towards the nitrogen. Okay, even the hydrogens are going to have some polarity going towards the hydrogen like that. I mean, towards the nitrogen. So this is going to be more, there are some bonds which are polar in this substance. And obviously, hydrogen fluoride, if you consider the last one, this is polar. The bond between hydrogen and fluorine is a polar bond. Why? Because fluorine is the most electronegative atom. So you see that this one and this one, they are both having polar bonds. Because they've got polar bonds, they can exhibit, and they are also having hydrogens, they can exhibit hydrogen bonding. All right. So that is what we are going to consider. So molecules, you see a molecule like this one, BF3. This one is not going to be polar, but you have got three hydrogens. This is same with this one which is here. I mean, I've got three fluorines. Okay, most these substances like this, you might not see them polar because the way the bonds are going to be arranged, they're going to be arranged in a trigonal planar. You have got the middle one, you have got this here, you have got here, and then you have got here. So these are able to cancel themselves out, the dipoles. All right, sorry for that. Okay, question number 18 here. How many pi bonds are in the molecule below? Now, one thing we need to know is that a double bond has got one pi bond. So there is one pi bond here, there is one pi bond here, there is one pi bond here, one pi bond here, and then a triple bond has got two pi bonds. So there are two pi bonds here. So 1, 2, 3, 4, 5, 6. So we have got 6 pi bonds. Okay, pi bond, a double bond has got one pi bond, a triple bond has got two pi bonds. Question number 19. What is the hybridization state of the nitrogen atom in the molecule below? What is the hybridization state of the nitrogen molecule? Now, if you look at this nitrogen, it has got a lone pair 1, it has got a bond this side 2, it has got a bond this side 3, another bond this side 4. Whenever something has 4 bonds, the hybridization is sp3. Okay, not only bonds but including also a lone pair of electrons. So the hybridization is a 3. But if it was something like this, here we consider 1, 2, 3. So the hybridization is going to be sp2. So for this one, it is sp3. Question number 20. Name the two functional groups circled in the molecule below. The two functional groups circled. So if you get to look at this one here, you have got, there's a carbon at this point, and then you have got an oxygen, and then hydrogen. This is a carbonyl functional group. Now, a carbonyl functional group can either be a ketone or an aldehyde. Okay, a ketone is found at the end of the chain, and an aldehyde is found on the middle of the chain. So identify which one is going to be. Okay, we're going to identify what functional group that is going to be. And then if we look at we look at this other one, which is here, we have got a carbon here, and then we have got oxygen alone, we have got another oxygen, and then an hydrogen. This COOH, this is a carboxylic acid functional group. So obviously this is not going to be it, and this is not going to be it. So the only two possible answers which we have is C and D. Now, since for a ring structure, we don't have the end of the chain, okay, like it is always on the middle. We don't have like this is the end of the chain, it is always on the middle. Then such a functional group, okay, so if we get to look like at on this functional group which is here, it is outside the chain, right? Like it is bonded like that, it is outside the chain. C double bond with O and then H. So this is at the end of the chain. That is going to be an aldehyde. But if it was on the middle of the chain, for example, it was something like, let's say it was something like this, and then this carbon which is here now has got a double bond with oxygen. This obviously would be a ketone because it is on the middle of the chain. Alright, so that is an aldehyde and a carboxylic acid. So that is going to mark the end of section